So far, we've been doing okay writing 6808 machine language programs for the Heathkit Hero Jr. robot on paper and hand assembling them into runnable hexadecimal code. But our programs have been very short so far, as we learn the basics of how the robot works. Now it's time to upgrade our development environment. I want to write longer, more complicated programs for the Hero Jr., and for that, we'll need to use a cross-assembler running on a modern computer. What's a cross-assembler? Good question. A cross-assembler is a program that runs on a machine other than the one you're writing programs for. It takes a program written in mnemonics, those short human understandable words like LDAA and JSR, and converts them into hexadecimal numbers that can be loaded and run by the target machine's microprocessor. While there is an historically accurate cross-assembler for the 6808 from Motrola that runs under plain old DOS, I don't feel a need to be that historically accurate as I'm developing software for the Hero Jr. Rather, I'd like to use a modern, easy-to-run, and actively developed cross-assembler that's available for my computer, a Macintosh, and for Windows as well. That way, these videos will be accessible for folks on different sorts of machines without the need to run DOS in a virtual box and other such shenanigans. The cross-assembler I'll be using is called CRASM, short for cross-assembler. It's available for both Windows and Mac and can assemble programs for several target microprocessors, including the 6800, which is instruction compatible with the Hero Jr. 6808. To use it, we'll need not just the cross-assembler, but also a terminal emulation program to let us interact with the robot and load program files, and we'll need a text editor of some sort to write programs. We'll also need to learn how to run the assembler from the computer's own internal system terminal, which is different from the terminal emulator we use to talk to the robot. Installing CRASM is mostly straightforward with only a few bumps along the way. It's distributed as source code, so first we visit the project's GitHub. To download the latest version, which right now is version 1.8, we click the big green Code button and select Download Zip. I'll save the file to my desktop and then unzip it by double-clicking. This gives us a CRASM master folder with the source code for CRASM. When we compile the source code, our system compiler software will follow the instructions in this Makefile. Because of increased security in the Mac's operating system, we need to make one small change to the Makefile before we continue. I'm opening it in Code Edit, but you can use any text editor. And the small change is to add /local to this prefix variable. Basically, OS X on the Mac no longer lets us easily install apps to the main binary folder, but we can still install to the local user's binary folder. Now we need to compile the source code into an executable file and install it into the operating system. To do that, we need to download the Xcode development environment for the Mac. First, I open the System Terminal window and type Xcode select install, which will pop open this dialog window, allowing me to download and install Xcode tools, the command line programs from the full Xcode package. After a bit of a wait, that process is done, and we can use the Xcode command make to compile the executable. First, I type the cd command for change directory, and I can drag and drop the folder or directory I want to change to right into the terminal window. Now the Xcode make command builds the executable file. It reads the Makefile and follows the directions. Finally, we call make a second time with the install option to install CRASM into the operating system as an executable we can call from anywhere we like. The sudo command runs make as a super user, allowing it to alter the operating system. Calling CRASM with the -h help flag confirms the assembler is now installed. Now we can enter an assembly language program. Let's recreate our Hello World program from Part 4. Back in Code Edit, I've created a new Hero Jr. folder and a blank text file called hjr.asm, so we can start to re-enter the Hello World program. As we go, we can compare the original handwritten version to this new assembly language version. First, I enter a few comments. The semicolon character marks the start of a comment, which holds until the end of the line. Here, I'm using 4 semicolons to indicate the comments at the start of a program. Comments like what the program is, who wrote it, and some details about the Hero Jr. robot it's supposed to be run on. Next, I'll tell CRASM which microprocessor this source code is for. The CPU 6800 targets the Motorola 6800 family, which includes the 6808. Now the code keyword tells CRASM we are starting a new section of code. This helps it keep track of variable names and memory locations. Our program will use only one code block. Now we come to equates, which in higher level languages would be the variables section. We define some labels and give them values with the equal sign. Phrase address 1 is the variable where we store the address of the phrase we want to speak. And save phrase is the address of the ROM routine that speaks the phrase. Now we come to our first routine, announce. This is the one that calls save phrase and then waits for the voice synthesizer to finish speaking before returning. We need to tell CRASM where to put this routine in memory as it assembles the mnemonics. So we use the *= command and give it a starting address, 0800. Now a new label to mark the start of the routine, announce. As CRASM assembles the program, this label will automatically be set to the address of the JSR instruction. So announce will end up being equal to 0800. Next, I'll type the mnemonics of the program, pretty much as we had them in our handwritten listing. But notice here I have added a new label, L001, so that a few lines later I can target the BNE branch if not equal instruction back to the right place. On the paper listing it's shown as just an arrow leading back to the LDAA instruction, but the assembler needs it explicitly indicated with a new label. Next is the Hello World routine proper. Notice that I use another of the *= commands to reset the starting address to 0810. When CRASM does the assembly, it will take care of putting Hello World farther down in memory at the new address instead of right after announce where it normally would. I've included a label for the start of Hello World in case later on we want to add other routines that call it by name. Again, the rest of the mnemonics are pretty much the same as the paper version, except we're directly using the labels we've created to refer to different routines, addresses, etc. Finally, I'm adding the phrase data itself with a label, HW phrase, that matches the one I used in the LDX instruction up at the start of HWorld. These DB commands are pseudo-ops, which look like assembly mnemonics but are actually instructions to the assembler. DB stands for data bytes, and the following values, separated by commas, are just placed directly in memory by the assembler. To finish things off, we'll use the code command again to mark the end of the program. We can save the program and switch back to the terminal to assemble it. I'll use CD to change directory again into the Hero Jr folder I created earlier. It contains just our ASM source code file. CRASM hjr.asm starts the assembly, which happens very quickly. If we scroll back, we can see the output from CRASM, including the fact that we had 0 errors and that assembly completed successfully. But we don't yet have a file we can transfer to the Hero Jr and run. For that, we'll call CRASM again with a -o object file directive. Here I'm telling CRASM to save the assembled hexadecimal numbers into an S19 file. This is the Motorola file format created for microprocessors like the 6800, which the Hero Jr.'s RS-232 monitor program knows how to load. Opening the file, we see a few S1 records, which are the lines that contain a starting address for each block of numbers and the hex value to load at that address. Notice the 0800 address for announce and the 0810 address for Hello World. There's also a 0820 address, since Hello World needed more than one line of hexadecimal values in the S19 format. Finally, this S9 record on that last line tells the monitor that it's loaded the entire program and can stop. For the Hero Jr, everything after the 9 is not needed and can actually create some weirdness with the monitor program, so I'll just delete it before saving the file. So now we do have a program we can load into the robot, but we need to connect the Hero Jr to our modern computer with a USB to serial cable. This cable basically translates from modern USB on one end to ancient RS-232 on the other. This one even has an adapter to go from 9-pin RS-232 to the 25-pin connector the robot uses. With the cable in place, we run a terminal emulation program to pretend to be a serial terminal. just like the term program we would run on the TRS-80 Model 100 in previous videos. I use CoolTerm on the Mac, and for Windows you'd use TerraTerm. I have a settings file that matches the 7none1 RS-232 settings of the Hero Jr. serial port, and with the software connected, we get the D prompt as usual. If we use the M command to look at location 0800, we see that the RAM contains all zeros initially. The L command tells the Hero Jr. to load a program file from the serial port. Now we choose Send File from CoolTerm's connection menu. Click OK for raw data, and then choose the S19 file that CRASM generated. And voila! We have now transferred the machine language program into the robot. Using the M command again at location 0800, we see that we no longer have all zeros, and the I command shows us disassembled machine language instructions in memory, matching our original program, just minus all the convenient labels and comments. And lastly, we can set the program counter to 0810, and use the G command with 0819 for the return address to run Hello World.
Hello World.
And there we have it, a fully functional cross-assembler on a modern computer which produces 6808 machine language programs we can transfer to and run on the Hero Jr. This simple step will open the way for much more complex programs in the future. Next time, we'll finish our look at the Hero's keypad input routines, and in later videos we'll start to explore sensor input and motor control as we teach the Hero Jr. some new tricks. Join us next time as we continue our restoration of everyone's favorite 80s robot. And if you like this video, don't forget to
like, subscribe, and ring the bell.